In this video, we're going to look at the small signal analysis for BJTs, and we're going to consider NPNs for the time being. So in addition to the large signal analysis that we saw in the last video, we can also do a small signal analysis. So what we're going to do is consider some base current that's going to have a DC component and then an AC component. Preferably, we'd like to say that that AC component of the base current is going to be quite small. And we're also going to have VBE, so the voltage between the base and the emitter, also as a function of time due to having a DC term and then this AC term, again, quite small. So we're going to use the Shockley equation that we're familiar with, and that's going to give us the base current and then the exponential that we're familiar with, where VT was your thermal voltage, and again, that's about 26 millivolts at 300 degrees Kelvin. So in the case of the small signal analysis, we say that this IB right here is capital IB DC, and then that small AC component. So how we modify the Shockley equation? Well, it's not too different, except this VBE, as a function of time, gets expanded in terms of the DC and the AC component. Now we're just going to apply a common property of exponentials. So inside these brackets, we can express this term, which is right here, as the product of these two exponentials. And that's simply just going to allow us to plug that back in for our original equation that we're looking at right here. So we have, again, our total base current, and we just split up these exponentials. We also took this 1 minus alpha and distributed it to this minus 1 right here. So that's how we get that last term. Now, recall for the purely DC case, where we don't have that AC term, this is what our base current is equal to. And for VBE divided by VT, or that thermal voltage, if it was greater than 2, we made a very bold approximation that this exponential, where we had this minus 1, was approximately equal to just that exponential. So we're going to take that approximation and do the reverse now. So inside what we had for right here, what we're going to do is evaluate that right here, and you're going to end up with the minus 1 inside of this term. So that's where we added that. Now, what we can do from this term is actually call that the DC current for the base. So that allows us to say that the total base current is approximately equal to the DC base current, and then we have this exponential that comes for the ride. Now, if beta is much, much greater than 1, alpha is approximately 1, and we keep going with the approximations. Why stop now? So this leads to the total base current being approximately equal to the DC base current, and then we have this exponential here. Now you may ask, how many more approximations can we do? Well, we're really going to push the limits with this one. So now we're going to make the approximation that e to the x is approximately equal to 1 plus x, and that allows us to say that the total base current is approximately equal to the DC base current plus the DC base current times the AC part of VBE divided by the thermal voltage VT. Simplifying this further, we can get rid of this DC part of the base current right here, and that's going to allow us to say that the AC part of that base current is approximately equal to the DC part, and that's going to be multiplied again by the AC part of VBE divided by the thermal voltage. Now we can actually rearrange this such that we get the small signal AC part of VBE divided by the base current, and that is going to be approximately equal to the thermal voltage divided by the DC base current. And we actually define that as something called R pi. Now in terms of the collector current, that's going to be equal to beta times the small signal for the base current, which is going to be equal to beta times the base to emitter voltage for the small signal divided by R pi. Now, just as a side note, you may see the transconductance defined, G sub m, as beta, or the gain divided by R pi, which is equal to the DC collector current divided by the thermal voltage. And the reason that we've done this is because now we are able to express the NPN transistor simply as kind of this resistor with this dependent current source. So there's a few models you might see. The first one is here on the left. So we have R pi, and then our current is beta IB. So we have our base right here, our collector, then our emitter. We still have VBE, but notice this is the small signal component. Now perhaps a less common thing that you'll see is that current source represented by the transconductance times VBE. And perhaps you're asking, why do we need to even have these things to begin with? So what we're going to do is kind of branch into the next video, and we're going to consider an amplifier. Now this amplifier uses an NPN transistor, and there is an AC source, but you'll also notice that there is a DC source. In addition to these sources, you'll notice that there are some capacitors in this entire network too. So not only do we have a DC component and an AC component, we also have more components than just resistors, and we're going to try to find some output voltage. So how do we really evaluate this? Well, we have to consider two cases. The first is going to be what's happening in the DC case, and when we figure that out, if we scroll back up, the reason this is important is because R pi is defined from the DC case. So if we're able to find the base current in the DC case, we should be able to define R pi, and that allows us to then do the AC analysis. So this may seem like a lot of back and forth, and to some degree it is, but in the next video, we'll see how you can actually do this analysis. Thank you for watching. We'll see you there.